In the last video, we couldn't quite finish out this example, so let's finish it out now. Remember that we have a binomial experiment where n is 15, because you're looking at 15 random patients, and the probability of them being over age 65 is 0.53, so that's your probability of success. So down here for part E, we want the probability that more than 10 of them are over age 65. So let's see what more than 10 would look like. Okay. Let me lose my earlier highlighting here. I'm going to go with more than 10. So if I want more than 10, that means I want 11, 12, 13, and so on, right there. All right, so I want the probability of more than 10. I want 11 or more. So what I'm going to do is I'm going to find, again, the white region above what I just highlighted, and then take it away from 1. The cumulative distribution function, the CDF, always starts at 0, always. You can't avoid it. So if it's going to start at 0, I want to basically tell it to stop at 10. Then I'll take it away from 1, that number I found, away from 1, because I know that the entire column must make 1. So if the whole sum of the whole column is 1, take it away from 1, and I'll have take this portion from 10 and below away from 1, and I'll have what the green portion must be. Okay, so more than 10, so it's 11 or more. That's 1 minus the probability of 10, less than or equal to 10. So I'm going to do CDF. CDF is the less than or equal to. So I'm going to say start at 15, or n is 15, 0.53. You're going to start at 0 and you're going to end at 10. And now let me do this with the calculator. So let me clear this out and just remind you, second distribution, it's above your variables button. And then go up to the very top and it kind of takes you to the bottom of the cycle. And you want, in my case, alphabet B, but it might be different for your calculator. So 15 is my number of trials, 0.53, and I want to tell it to stop at 10 this time. I'm going to go down to paste and press enter. And then I press enter again, and I get 0.90, well, 9080 if you're rounding to 4 decimal places. Because the 6 rounds the 9 up, the 9 would round, see how this is 79 here? Basically the 6 rounds the 79 up to an 80. So it makes it 0.9080. And then you take that away from 1. So you go 1 minus that answer, and you have 0.0920. Just on a side note, you can actually do this all at once. 1 minus, then I go to the binomial, and I grab the binomial distribution CDF. I say 15, all that stuff, good stuff, paste. You can actually do it all in one fell swoop, right? Rather than separating it into 2 separate parts if you so desire. And that would give you 0.0920. All right, now, last part. Would it be unusual if all of them, see that, all of them? That's an interesting one. All of them would mean all 15. So what I'm really asking about here is the probability that all 15 people. That's these 2 parts, this part right here at the very, very bottom. Right there. So that's an exact probability I'm asking about, all 15. So I want to find the probability that x is equal to 15, and that's a PDF again. P for probability distribution, right? PDF. And there's 15 trials. The chance of success is 0.53, and I want all 15. So let me show that to you with the calculator. So it's distribution again. I'm going to go to binomial PDF. And actually, let me just show you real quick. It's the alpha key. If you get down here at the alphas, so you go alpha A, and that's binomial PDF. See it right up there? And it's 15.53, and I want 15. Press enter on paste, press enter again, and now that's scientific notation. That's 7.3 e negative 5, exponentiated negative 5, which means the decimal is set 5 spots to the left. So that'd be 0.0007. 0.00007. Sorry, not enough zeros there. So let me just remind you how to do this part from back in school sometime. Originally the 7 has the decimal point right here, and then you move it 1, 2, 3, 4, 5 spots over to the left. Put the decimal point right there, excuse me, and there it goes. Okay. Would that be unusual Well, yes, it would, because that probability is less than 5%. Less than 5% is unusual. So yes, I shouldn't say this. All 15 patients over age 65 would be unusual, as the probability of this is less than 5%. Alrighty then. We're finally done with that example. Now let's move on past the binomial formula for just a minute and talk about some other nice things that happen with the binomial probability experiment. Because the binomial probability experiment follows very particular patterns, it gave us that formula for probabilities, which is lovely. It also gives us very simple formulas for the mean and the standard deviation. But these formulas only work if the experiment is a binomial random experiment. Okay? If it doesn't satisfy all those properties of a binomial experiment, then these formulas will not work. But if they do work, they are nice and easy to use. And of course, as usual, you don't have to memorize them. You can put them right on your note sheet for your exams. So it's just a question of using them when they're appropriate. So again, let's consider this same report where 53% of people are over age 65 if they have coronary bypass surgery. We have 15 random coronary bypass patients. What's the mean and the standard deviation, and interpret them in context. So the mean is n times p. So n, if you remember, was 15 and p was 0.53. Let me bring those back. There we go. N was 15, p was 0.53, q is 1 minus p, which is the probability of failure, is 0.47. So the mean is mu sub p, or excuse me, mu sub x, which is n times p, which is 15 times 0.53, which is 7.95. If you don't believe me, there you go, 7.95. Now the standard deviation, if I could spell it right, is equal to sigma sub x, which is the square root of n times p times 1 minus p. So let me type that up. It's right here. So let me go find it for you so I can show you how I did it. In this calculator, you hit the square root part first. Then you say 15 times 0.53 times 0.47. And you get 1.933. And remember, the 0.47 came from 1 minus 0.53 in the first place. So you get 1.933. Now, what does this mean for this particular experiment? How do we interpret the mean and the standard deviation in this context? There we go. In a random group of 15 coronary bypass patients, it's very important that you say the n value somewhere. So in a random group of 15 coronary bypass patients, we would expect 7.95 patients to be over the age of 65, give or take about 1.933 patients. I should say, I guess, the word approximately. We would expect approximately 7.95 of the patients to be over the age of 65, give or take about 1.933 patients. And that's it. So very simple formula for the mean, very simple formula for the standard deviation, very simple interpretation, which is very similar to what we did in chapter 3. Just don't forget to put your n value in there somewhere. All right, now what about a binomial probability histogram? So we can make histograms of those binomial probability distributions. Let me bring that in. So this is a histogram of our coronary bypass patients. So you can see right here is the probability of 9 that you found earlier in an earlier problem. And this time we want the probability that exactly 12 of them, right there, are over the age of 65. So remember, exactly, that's a binomial PDF. So what you're looking for here is the probability of x is equal to 12. So that would be binompdf. 15 is still your n. Your probability of success is 0.53, which you can see actually at the top right here. It says it's a binomial distribution. N is 15, p is 0.53. And then let me check my numbers there. So if I go to second distribution, and then I happen to know PDF is letter A, but if you don't believe me, you can see it right there. It's letter A. So I'll hit alpha A. And I want 15 still. I want 0.53, but I want exactly 12. Enter. Enter. and I got 0.0232, which is what I typed up. So that's convenient. And that means that this little bar right here is actually 0.0232. So let me draw that. I'll be right back. There we go. So I've got that little bar labeled right there. So that's 0.0232. And you can see that this histogram is a distribution that would show the values for each of these table values. So this one right here we found was 0.1780. This one you just found was 0.0232. And that histogram shows you all of the individual values in a graphical form rather than in a table or in a formula. It gives all the PDF values. So let me type that up. There we go. This graph is a representation of all the possible x values from 0 up to 15. And it got cut off at 14 because the probabilities for 15 are so very, very, very small, as we discovered right back here. Very, very tiny. But nevertheless, it's a graphical representation of those values and their individual probabilities. For example, it'd be binompdf 15, 0.53, x, where x is 0, 1, 2, 3, and so on. Let's stop right here, and in the last video I'll tackle the last two examples, which are comparing probability histograms from different experiments with different p-values. So I'll see you back here then for that last part.